I've been making my presentation on efficient locking for concurrent operations on B trees by Philip L. Lehman and S. Beng Yao. Okay, so there are several applications of B trees, and some of the main ones are they are used by database systems for storing large volumes of data. They reduce disk operations, and they have a runtime of 0 log n for many operations. I'll soon elaborate how all this works. Okay, we all know that a storage of a computer has there are two main storage when it comes to a computer. There's the primary storage and the secondary storage. The primary storage is normally the RAM. They are made of silicon chips and are fast and expensive. The secondary can be any form of disk drive or a solid state device and are relatively slower and cheaper. Okay, so normally with a B-tree node, B-tree nodes normally equivalent to a disk page. So we can see that this node here is equivalent to the disk page. The roots is normally assumed to be kept in main memory. So when we want to load a key, probably a key from a leaf node, what we normally do is, let's say we want to load key 47. We start from the roots and we realize that it's greater. We go to this internal node here and we load into the main memory. And then we finally load this desired key into the memory. So we can see that in total, we make 2 disk operations. This is why earlier one application was stated that it reduces the number of disk operations. And this is why many database or many applications are using B trees, because B trees are useful for storing large data, as you can see how they minimize storage and all that. Now, the basic concept when it comes to B trees, let's see how this works. This was taken directly from the paper. I'm not going to waste time and read all this, but I'm going to elaborate how this whole concept works. Okay, this is a tree structure. We already know what the roots is. Okay, these are the internal nodes. These are the leaf nodes, and this is the root node. Simple when it comes to a tree structure. Now, each node has n keys. So when we look at this node, it has 3 keys. The nodes are normally aligned in an ascending order, as you can see. So each single node is automatically sorted out, and I always in an ascending order. Now, each node has n plus 1 children. So this node has 4 children, and the other one has 3 children, as we can see. Okay. Each pointer determines the leaf node. So this pointer basically means that the nodes in the leaf node are lesser than 40. So each pointer, same here, each pointer indicates the values in the leaf nodes. All leaves have the same depth. The lower and upper bound on the number of keys. Okay, let's see the minimum degree of the T. For a B tree, the T should be greater or equal to 2. T is minimum degree of the tree. I'll soon explain how all this concept works. Okay. Sorry. Now, the number of keys. T is normally used to determine the number of keys of a tree structure, and it should always be greater or equal to 2. Always, every tree structure. Okay, so the lower band, it should have at least T minus 1 keys. Every tree structure should have at least T minus 1 keys. And the upper bound should have at most 2 T minus 1 keys. This is the main concept we have to know. The internal nodes can be T children and at most 2 T children, right? So let's look at an example where T is 2. Here we can see that it has a 1 child because the minimum number of keys is T minus 1, and it can have a maximum of 4 children. Okay, So this is an example where t is equal to 2. It can have at least 1 keys, and the internal node should have at least t. As you can see, and the upper bound should have 2t minus 1, and the internal node should have at most 2t. When it comes to search, it's very simple. If you want to search for, let's say, key 41, what we do is we start from the roots. We realize 41 is greater. So we go to the right-hand side, realize 41 is between 40 and 55. We look at the pointer and find 41. Very simple. When it comes to insertion, let's look at a simple example of these two. This example is where t, the minimum degree t equals 3, meaning that the maximum number of keys you can have is 5, and the minimum number of keys we can have is 2, pertaining to the leaf nodes. So when we look at here, we see that the maximum number of keys is 5, so they are basically full. So we can't add an extra key if we want to insert 60. So what we normally do is we take the middle points and add it to the parent, and finally add our key, sort them out, and split it. We can either use 2-3 or 3-2 splitting. Here we apply 3-2 splitting, and this is the result. It's very simple, as you can see. One thing to know is that insertions is normally done to only leaf nodes. You can insert to internal nodes. And deletion, you can delete from any parts of the node, either being internal or leaf node. So let's look at it as an example. This is t equals 3, meaning the minimum number of keys should be 2 and the maximum should be 5. So if supposing you want to delete 21, if we take out 21, the minimum of keys is 2. It doesn't violate any constraints, so we can just take 21 off. This is a simple delete. Let's look at another case where, let's say we want to delete key 30. We look at the predecessor of 30 and realize there's 27. We replace the predecessors and take off 27. So 27 will replace 30, then 30 will go. As we can see here, delete 30. 27 will replace 30. 30 is out. Now, in case you want to delete 27, there's another case where the right child has t keys. This case was where the left child has t keys. So this case is where the right child has t keys. If you want to delete 27, we replace 37 by the successor, which is 31, and just take it off. Now, there's one last case where the internal nodes both have t minus 1 keys. And in this situation, if you want to take off 22, realize that we can't take from the predecessor or successor because they will violate the constraints. It should be at least 2, as you can see here. So what we do is we take 22 off and we merge all the keys. Very, very simple. So that's the concept of insertion, deletion, and search. Let's look at the problem at hand. Now, basically, this research paper is just trying to find an efficient lock for concurrent operations with the help of B trees. Okay. This is taken directly from the research paper. And let's just look at the situation. Suppose we have two processes, a search for a value 15 and an insertion of 9. Now, when you look at this, it's obvious that t is 2, meaning that the minimum has to be. It's obvious when we look at this situation, meaning we can't have more than 4 keys here when we look at this tree here. Okay. So when we want to insert and search at the same time simultaneously, obviously, if you try inserting a new key to our leaf, it will modify the whole structure of the tree. So assuming the processes are being performed simultaneously, and we locate this pointer, both processes locate this pointer, you realize that if insertion takes place first, insertion will alter the whole structure of the tree. So when the search comes in, the search will not be able to find the key and will produce an error. So this is the problem at hand, performing several operations at the same time. So this is a simple algorithm, also directly taken from Sorry. Also directly taken from the research paper. And as you can see, maybe when we read C and we read A and we examine C, we get pointer to Y, examine A, gets pointer, insert 9 into A, must split into AB, put BY, put AY, add node to the Y. And when C reads, C will get an error. So the problem is that the search returns a pointer to Y and then reads the page containing Y. Between these two operations, the insertion process has altered the tree, as we can see. Okay, now the problem is quite challenging. The challenge here, as you can see, the locking mechanisms, the atomic operations, and the set insert race conditions, and the two-phase operations. Let's look at related works. Previous works, one early work to this problem was Samidi's approach, which exclusively locks the entire path along with the modification might take place. So his strategy locks the whole path of the tree. Now, with Bayer and Skion's approach, it locks just the upper section of the tree with writers exclusion locks, which only locks out other writers, but not readers. So his was an improvement, but with his approach, you still cannot perform two write operations like maybe insertion and deletion, or maybe insertion and insertion itself. Okay. Now, Miller and Schneider's approach was quite a good improvement, which employs the pioneer and followers locks to prevent other processes from invading the region of the tree. So the locked region moves up the tree, performing appropriate modification. And followed by our proposed approach. Sorry, there's supposed to be an arrow here. Our proposed approach, which is the B-length tree. Our proposed approach, the proposed approach in this research paper, is an improvement of Miller and Schneider's approach, but just locks smaller section of the tree. That is our approach. It's just an improvement of this, but locks smaller portion of the tree. Let's see how our approach works. I'm not going to waste time and read all this, but okay, let's just read the headings of it. Introduction of link pointers, chaining nodes with link pointers, purpose of link pointers join node splits, temporal fix for correct concurrent operation, efficiency consideration, and additional advantage for serial searches. I'll soon demonstrate all this. Let's look at a simple toy example here, okay, of how all this occurs, and after that, I'll show an actual example for us to further understand this. Let's consider three nodes, A, B, C, at the same level, okay? This B-link tree structure has a pointer connecting to nodes at the same level. If node B split due to an overflow, B1 is the new first node, and its links to pointer B2. B2 takes old link pointer of B, forming a functional link like this. That is like a simple toy example to understand, but we'll soon explain it. I'll soon explain how everything works. This figure is taken from the research paper for us to see the structure. So we can see that there are pointers. The only difference between the normal B tree and the B-link tree is there are pointers connecting nodes of the same level, which is quite amazing. We'll see why it's amazing anytime soon. This algorithm is from the research paper. I'm not going to waste my time to read it, but let's see an actual toy example for us to further understand this. Okay, let's say we want to run two concurrent operations, search for key 7 and insert key value 8. Obviously, we know that key value 8, looking at this, if the maximum capacity constraint is 4, obviously, when we insert key value 8, it will alter the whole structure of the tree. So we can see that when we insert 8, this is what will happen. Now, if the processes are running concurrently, the search will also be at this point of the tree, and it's not going to find the value 7. So with the help of the link pointers connecting nodes, we can see that if we search for the maximum and we don't find 7, we just search for the link pointers and search through, and you can see 7. So you can see that these two concurrent operations can run smoothly without even doing any lock here. When it comes to search, there's even no need of using a lock. Now, let's look at an example with two write operations. Say we want to insert key 7 and delete key 97 at the same time. We can see that 7 we can find 7. If we want to insert key 7, we can say that the structure of the tree is going to be altered here, obviously, from our understanding of how the basic concept of tree structure is. And we can see that if we want to delete 97, we can just delete 97. Sorry, there's supposed to be an arrow here, but we can just take off 97 and also insert key 7 at the same time, because with our approach, what we normally do is we lock the parents and lock our current node. If the maximum number of locks that can occur in our approach is 3, and that is a situation where if the parent node is full, it also has to undergo a splitting. So we lock that parent node being splitted and we lock the child node. So you can see that we make use of locking less, using less number of locks in our operation, aiming to be able to perform several operations. So that's the powerful approach of the B-link tree structure. Okay. Now the contributions to this is the introduction of the B-link tree structure. And it's also an additional efficient search algorithm, because now we can search through nodes at the same level because there's a link joining all these nodes. We don't need to just search and traverse back and search and traverse back. Since now there's a link structure connecting all the nodes at the same level, we can read and write algorithm with deadlock freedom, and optimization for locking limits the number of lock nodes during certain operations, ensuring efficiency and minimizing potential bottleneck. And this is an overall improvement in concurrency. So that is basically the concept of this research paper. Thank you.